Okay, any questions before we start? You know, I sent out a couple emails about given that people move in and move out so much, the first week is sort of intro, and then I'll have like your first assignment will be starting next week, and they'll give everybody time to sort of figure out, you know, your schedule. Any questions?
Oh, I have a question about that VART thing. Is that not going to be accessible till next week?
What I'll do is the VART thing will be one of your quizzes, so I will set up a quiz and give you a link to the VART. I mean, most people probably already looked at it anyway. Just, you know, Google VARK. It's the first thing there. But no, I just wait. Just based on experience, people are moving in and out, and no one knows their schedule. So if I want to set up especially for online students, want to set up a time for people to meet online, or even in class first weeks. Usually it's just such a mess for everyone. So yeah, and then I'll have several just sort of practice online sessions on the Google Hangouts, and so everybody can sort of see. And you know, I think most, if not everybody that's taking the online section are actually on campus. So, you know, for review sessions, there's no reason you can't come. And if you're in an online section, you can still come to class. It's basically, you know, like I said, my philosophy is that an online class should be as close as possible to being in the class and not be a totally different experience. So, okay, any other questions? Okay, we're going to start today with something that you'll be using throughout the semester, and that is basically graphs and data. And I always like to start with how we look at things, and not just in science, but you know, in day-to-day life. More and more, you read things or see things. One of my favorite was a few years ago, and there was, I can't remember what news show it was. Well, it was on all the news shows that broccoli seedlings were great for you because they had a lot of compounds in them that were anti-carcinogenic or whatever, so it would sort of eat broccoli seedlings and you're not going to die of cancer. Then Friday of the same week, there was another piece on all the media outlets about how eating broccoli, how broccoli had carcinogens in it. So if you eat broccoli, you would get cancer. It was the same compounds. Exactly the same compounds. And one thing you'll learn, especially when you're dealing with life systems, is a lot of times a little of something may not do anything to you. A little bit more may be promotive, and then a lot more could be damaging. So you're bombarded by all this stuff about disease, like this reduces your chance of getting X kind of cancer by 25%. Well, what does that mean? You know, let's say it reduces the chance of getting breast cancer by 25%. How many of you people in here need to worry about that right now? You know, it's not 25%. It's 25% of sometimes an incredibly small percentage to start off with. But we're trying to get grant money, so we're going to say 25% and not reduce your chances from 0.01% to 0.075%. So, you know, when you read the paper, you know, you've got to, or online, read the paper. Nobody reads the paper anymore. So anyway, we want to start with this today. And and I don't know if I'll get through this today or not, because I'd like to use a lot of examples. Okay. If you take a plant, take two plants, put one plant here in the light, or put it in the greenhouse, put the other plant in a greenhouse in a black box, what happens to the plant in the black box? It dies, without you even looking at it. Okay, why does the plant in the black box in the greenhouse die? Needs light. So the lack of light is what kills it. No. What's the first thing that kills it? You're right. It needs light to survive. Lack of sugar is from photosynthesis. What else? Could be heat. It could be inside a black box and gets a lot hotter. Absolutely. If the outside of the box is black. Airtight. If it's airtight. No oxygen. What else can kill it? Water. Yeah. So the point is, you really don't really know all of the parameters. So if I put it in a black box, let's say I cover the outside of the black box with aluminum foil, I remove the heat problem, and then I have a tube going into it so that I can add water to it, then the plant is going to die because it doesn't have any photosynthesis, it can't produce sugars, and it dies. So there are a lot of assumptions that we make. And when you're doing science, assumptions are really a big problem. You have to know all the parameters. You know, here's another one. You've got a light in your refrigerator, right? You open the door, the light goes on. When you close the refrigerator door, what happens to the light? It goes off. How do you know? You push the button. But on the newer refrigerators, the switches are actually those, what do you call them? They're electronic, so there is no button to push. So how do you know the light goes off? I mean, yeah, we know it does, but has anybody ever done the experiment? I mean, can you open it and close it fast enough, faster than the speed of light, to see if the light goes off?
Get in there and close it. And
Get inside your refrigerator, close the door, and see if the light goes off, or put a sensor. You know, put your phone in there. Turn the phone on, you know, have the phone start making a video. Lay your phone in. Just think of that technology you have carry around with you now. You can answer that question in a few minutes. Start taking a video, set your phone inside, close the door, wait a few seconds, open up, look at the video. You know, I mean, you carry a tremendous number of sensors around with you all the time. So there are assumptions, and when you're doing science, that's the killer. You know, so if I put a plant in the light and I put a plant in the dark, if I don't water the plant, then I can say, well, the lack of light killed the plant. That's not right. Could be, could well be. But we sort of have to keep everything but one thing the same. Okay, so most of the time when we set up experiments, everybody knows what a control is. We're going to be talking about controls. We'll have more than one control. You know, and then when I have a lot of students that do projects with me, do lab projects, and the first thing I have a student do is to sit down, go to the don't go to the library, go online, look up some papers, and sort of see what people are doing before they actually start an experiment. Because you sort of have to think a lot about what you're doing, because you could be wasting a lot of money if you don't do, you know, the appropriate thing. So here's sort of the overview. You know, we still talk about the theory of gravity, but I'm pretty sure gravity really is. You know, so, but we really don't completely understand gravity. At least I don't. You know, and so we still don't understand it completely. So, when you see something online or whatever, you sort of have to worry about whether or not it's real. And you'll see all sorts of this will help you do this. Take this medication or take this herbal extract and this will do what, And it's actually based on published research, and it's a paper. One of the better ones I like is there's this really expensive cofactor, and you'll learn what cofactors are in a couple of weeks or maybe even sooner. And they gave 3 people the cofactor. They did not give 3 people the cofactor, the control group on stationary bikes. And then they tested their how fast they could go or something like that. And guess what? The 3 people that got the cofactor, I don't know if they had longer endurance, I don't remember what it was. And they published that, and so now the company put that in as published results show that this works. No. And I'm giving you the take-home message, but what I'm going to be covering is that you have to do it again and again and again and again and again. Okay, here's something you're going to see this. You're going to see this curve over and over again. This is real-world data. It's called the Warburg effect. And the growth of plants, most plants, and we're going to talk about C3 and C4 plants. What does this curve show you here? Relative rate of CO2 uptake is going up, and across we have oxygen concentration. So what are we looking at here? As the concentration of oxygen increases, what happens? The CO2 uptake decreases. Because for 90% of the plants out in the real world, oxygen inhibits photosynthesis. And you know that as something called a C3 plant. And you're going to learn the chemistry behind why that works. And it's a real world thing. It's not a lab thing. If we could convert plants to being C4, plants would be a lot more efficient. And you're going to see when we talk about enzymes, then we talk about photosynthesis, that this is one protein. This is the protein that fixes carbon dioxide, grabs carbon dioxide, and adds it to carbohydrates. And guess what? That protein not only sees CO2, it also sees oxygen, and it grabs an oxygen molecule every once in a while. Every time it grabs an oxygen molecule, no carbon is added to the plant. Okay? Yes, sir?
Isn't it because at higher temperatures, the CO2 is it's less available and more oxygen is, or more atmospheric oxygen?
That is part of it, but it is more basic. This is the most common protein on the planet. It's called rubisco for short. And that protein, if you squint your eyes and look at it, then CO2 and O2 looks just like it. Looks like the same thing. Why does cyanide kill you in so many great ways? Cyanide looks just like oxygen to a lot of enzymes. Same thing. So, you look at this and you will have graphs like this, not even probably pertaining to science on your exams. Interpreting data is very, very important. And then, what if though? Okay. Now, if you've had winemaking with me, you've seen this before, and I use this in my graph. This is my favorite all-time graph. This is the rate of death from coronary heart disease and alcohol consumption. So what can you tell me? You have a non-drinker on the left, the next one's a former drinker, then we go all the way over to greater, that's a V, that's a greater than 9 drinks a day. We have black versus white, male versus female, smoke, coffee, or have a college degree. So what can you tell me? If you drink 9 drinks a day, more than 9 drinks a day, what's your chance of dying of heart disease? Compared to the non-drinker, which is arbitrarily set at a value of 1. So if you drink greater than 9 drinks a day, no heart disease. Exactly. Absolutely exactly. That's because you're going to die of something else. Okay, now this actually came from a pro-alcohol website, which they didn't mention that fact. Absolutely right. You look at this and you should just head over to the chicken and spend your life there, and you'll live longer, right? If you're drinking more than 9 drinks a day, what happens to you?
You don't do nothing.
You stay drunk.
What happens to you in terms of your life expectancy, though? Why does it go down? Accidents? Cirrhosis of the liver? Fights? You get killed in prison because you've gone to prison for your 10th DWI or whatever. You know, so just presented with this data, you know, you go, wow, this is pretty good. Okay? Let's go over to, if you have a college degree, you're less likely to die of heart disease. Why is that? Pay for health care. You have health care. Maybe you're making better choices. You know, it's so, you know, the point is you gotta take these things, especially as consumers. When I see a curve, the only thing I think of is why it's not true. Or why it may not be true, you know. And this is it. You got to question everything, you know. Now, anybody take a look at the, let me bring this, so actually I got these at the supermarket, and there's a link in today's lecture to the actual website. You know what these are, these green bags that you can put your produce in? They work. We put a banana in one of the green bags, and we put a banana inside one of the bags you get from the supermarket, you know, the really small, flimsy bags that you can get. And then, and I'll do a recording and put this online too. Sorry about that. Like I said, the first week, nothing ever works. There's always something that doesn't work right. And believe it or not, they seem to work. Okay? And so the question comes up then, well, is it the bag? Is it the kind of bag? And they're green. I don't know why they're green. Probably a marketing thing. So if you take and you put them in the green, if you put them in one of the green bags, the banana lasts longer than if you put it in one of those bags you get, you know, you unroll when you're at the supermarket. But what else could it be? And if you look up the green bags, they claim that they get the ingredient from some secret cave in Japan or something like that, you know, which I'm sure they don't. But what else could it be?
Started with the green banana in the first place. When that was not.
Yeah, you could, yeah, the banana. I didn't do any replications. We're going to talk about that. To really do this correctly, I'd have to have a lot of bananas in a lot of green bags, and a lot of bananas not in bags, and a lot of bananas in the supermarket bags. And guess what? Those supermarket bags a lot of those are not just plain old plastic. They're designed to actually keep your produce a little bit longer. So one thing you may not know, and if Dr. Cisneros can give a lecture on it, he's an expert on modified atmosphere storage, is when you go in and you see produce inside a plastic shrink wrap container, that's a special kind of plastic that is designed to modify the amount of oxygen that goes in and the amount of CO2 goes out. It's just not saran wrap. It's a whole industry. So we can put together some kind of an experiment. Okay, what could be that it's green? Probably not likely, but we could put some bananas in a green bag. Then we could cut the bag open and lay the bag on top of the banana and see if that does anything. We could do a lot of different things. Does anybody know why these bananas ripen like that? And be sure and watch the video. If you don't know, there's something called ethylene, and that causes bananas to ripen. And so let me tell you what the green bag does. It has something in it called permanganate, which is a compound that absorbs ethylene. Bananas produce more ethylene than about anything else. And so that bag probably absorbs a bit of the ethylene. Okay? And you do other things, like you may keep your bananas. Everybody ever seen all these banana hooks that you can hang your bananas up? Why do you do that? Airflow keeps the ethylene levels lower, so the bananas last a lot longer. Or longer, not a lot longer, they last a lot longer. Okay? So you can come up with, you can observe that phenomena, then you can come up with a lot of reasons why it may or may not be due to those actually sealed green bags. You have a green bag and it's open. And you could come up with all sorts of things you could do. You could take a banana in a supermarket bag, wrap it up, and put it in one of the green bags. Or you could do the reverse. You could take a banana, put it in a green bag, wrap it up, and put that in a supermarket bag. So you could just go on and on and on and on and on. With something as simple as that. Okay? So you see something, and you say, well, what are the reasons? Color. Can I get some green bags that are not green? I don't think the green has anything to do with the permanganate in it. I'm telling you why they work. But if you don't know that, what other reasons could you come up with for them not working?
Maybe like structurally the plastics are different?
Plastics are different, absolutely. It's probably actually a combination. It's probably kind of plastic too that changes the gas environment inside that plastic. There's a lot of money going in this. When you go to the supermarket now and you get all these pre-sliced apples, cut up onions, a lot of tech going into that, because you're too busy to slice an onion. So lot of tech. So there could be all sorts of reasons. You could put them in the refrigerator. Maybe there's not an effect then. So you could put them in the refrigerator, look at them every day. This is neat because we had a time-lapse camera that we could use. So in this case, in this example that I give you, it says that the green keeps the fruit and vegetables fresh. So if it's the green, what can we do? Use different kinds of green, see if green makes a difference. Like I said, we can take that green bag, we can cut it so that and then we just place the green on top of the banana. We know this isn't the reason, but maybe it's light going through and the green absorbs the wavelengths of light that causes the banana to ripen. We know that's not true. But at some point, somebody could have that, why do bananas ripen? Well, maybe it's because of light. And if we put bananas in the dark, put them in a container in the dark, they actually ripen faster because the ethylene builds up more. Okay. At some point, somebody probably did that. Okay? Now, let's talk about the actual terms about what independent variables are. And an independent variable, let's list a bunch of independent variables. What would be independent variables? What would we have to control to make this a valid experiment? Type of fruit? I went to the store. Actually, I had to go to the grocery store at like 6 o'clock in the morning to get some bananas that had just come in and were still, and by the time we even got them here, they'd already started turning yellow. Used to be the ethylene, they pick these bananas really, really green, and then they zap them with ethylene. And that used to be done at the grocery store. Now it's done in San Antonio at the HEB distribution center. So it's really hard to get bananas to do this experiment with, because by the time we get them, they're usually already ripe. So the kind of bananas, what else? Same stage of ripening. So, and we can actually, you can go in and I grabbed a bunch of bananas. So I assume they're the same kind. I assume they're about the same stage. What else? They're all there together, but it wouldn't be valid for me to have 2 of the bananas down here on this table and the other 2 upstairs in my lab. So they got to be, things we take for granted, but you have to really worry about. I mean, they've all got to be under the exact same environment except for what we want to look at. So we have a lot of these things called independent variables that we need to worry about. Same temperature, and they're all laying there on the table, so we're pretty sure. Got to be in the light because you're not going to be able to take pictures of them in the dark.
Would you want to go as far as like using bananas of similar weight?
Using bananas similar weight, and that's not a bad idea actually. Using bananas of a similar weight, or weighing the bananas and then coming up, and you can get these, by the way, you can get ripening charts for most produce, different kinds of produce. So you're right. So we could go to the extreme. We could have a little banana and a big banana. Would go, no, that's not right. So yeah, you go on and on and on. And some assumptions are okay. So if I'm going down to the supermarket at 6 o'clock in the morning, going in the back, and they're opening up boxes, and I'm getting those bananas out, getting all the bunches of bananas from the same box. They have probably all been exposed to the same amount of ethylene when they zapped them in San Antonio the night before or whatever, But these are all assumptions. So a lot of times we're thinking about, as a scientist, we're thinking about the trivial stuff. If you find a result that cures a disease, you better be sure that you've not overlooked something. And I'm being, it's a hyperbole, but if you do an experiment and you find a really important result, you just have to go back and check everything. I don't know, last summer, you've heard of the collider in, where is it? Yeah, the CERN, There were some experiments that indicated that there were particles moving faster than the speed of light. Okay, now that's just like, no, that doesn't happen. These were serious scientists, and they had collected data that said these particles were actually getting there before they left. So they published their data, A lot of people said, no, it's not possible. This, they published their results and they went back then to try to figure out, okay, what could go wrong? Now, that was like an extreme example of something because things don't go faster than the speed of light. And a lot of the physicists were just outraged that they had published this. They didn't publish it to say, hey, we found something going faster than the speed of light. They said, hey, this is what we measured. And then by publishing it, then if it's important, everybody's going to jump on it. And it came out, it was a piece of equipment that was, something about the equipment wasn't calibrated. I mean, and they tracked it down, but it wasn't trivial. They had to really go at this, to find out what it was. So the point is, if you have a result that's important, people are going to do it again. And that we'll get back down into some of the slides later. So we have the independent, and then the dependent variable is what we're actually trying to take data on. And the take-home message from this one slide is we have to measure something. We have to have numbers. Okay? And it could be you can have these things called firmness meters, which you use to you can put them on top of the banana and you can push it down and there's a gauge, and it measures the amount of force required to penetrate or to deform the banana. So the riper the banana, the less force. So you can't take your finger, squeeze the banana and say, yep, that one's softer than this one. Okay? I'll give that a 5. You have to measure something. And let me go on down here to a couple more here. Keep them constant. And I wanted to get this bottom point. It said bias. Okay, we're not supposed to want an experiment to come out a certain way. So if we go through what I just talked about, if I say, okay, yep, I squeeze this banana and it's a lot softer than this one, there's bias built into that. Now, we always want experiments to come out. Most of the time, we want experiments to come out a certain way. We have a hypothesis, we see something, we test the hypothesis. Sometimes we're just collecting results. Sometimes we want something to come out a certain way. And so we have to, as much as possible, remove bias. And there's even statistical ways to do that. Okay? And it can be, I can send you out in the field to measure, let's say, the color of tomatoes in an experiment. And I can give you a chart that has different kinds of red on it. Different. If you know anything about tomatoes, there's breakers, there's the green, there are breakers, there's pink. And that's fine, as long as you use the chart and look at the tomatoes and make a true, line it up as much as you can. That's fine. And you put down whatever that value is. So it could be 1 to 5. That's fine. But we have to have numbers. We can't feel that these bags work. The experiment that I showed you, and if you look at that video, sure looks like they work. We did that one time with one banana in each bag. So that's not a valid experiment. Okay? Questions? It's really, my first experiment I ever did was to collect good data that Santa Claus really didn't exist. You remember when you sat down, I assume do you write letters to Santa Claus or you do emails? I don't know now, probably emails. So what I did was I sat down with my mother one evening and I wrote my letter to Santa Claus about what I wanted. And then I got back up, I opened the letter, I took that letter out and put a different letter in. But what I got was the letter that I still had in my room that never left the house. I put a different letter with different things that I wanted from Santa Claus. And guess what? I got the stuff that was on the letter that I had hidden in my room. None of the stuff that I'd put in the letter that got into the mail, I didn't get any of those things. So that was pretty good evidence that mother must be Santa Claus. Mother and dad must be Santa Claus, you know. So, yeah, I was a weird little kid. So we have to replicate it. Yeah, boy. How come here's the letter. Now, you know, when you can't, you know, first I made sure I got everything I wanted. Then I said, well, look at this. How do you explain this? You know, and so, and then you measure, and and here is a place where I think we're probably going to stop today. We use statistics. We have to use statistics that are designed to where you can say this is different than this. This is statistically different than this. And that's based on math, and it has to do with populations. And if you do population work, you know, it's different doing work on you in here than it is on looking at seed germination in my incubator. I don't have to do as many reps in my incubator that's at a certain temperature, you know. And there's different sets of statistics. There's different kinds of statistics. So we're starting to do wine analysis where we're actually using people. You know, do you like this versus this and why? This kind of stuff. So it's a totally different kind of statistics. You know, people are harder to work with. And then we repeat. So I repeat it, get the same results, pretty close to the same results. It depends on what it is, then I publish it, and the big thing is other people have to do it. And they have to get the same results. And if they don't, that doesn't mean I faked anything. That just means they're getting different results, and we have to decide why. There was a famous experiment done a long time ago in the early 90s. There were two labs that were working with a certain aspect of photosynthesis about how many moles of light were needed for something to happen. And these were one lab was in England and one lab was in Champaign-Urbana, and these were the two top guys in that very small bit of photosynthesis in the world. One lab got 4, the other lab either got 8 or 2. I don't remember which way. They kept doing it, they kept getting 8 and 4. Okay? And they all both had solid data. Well, they ended up swapping their highly distilled water. So the Illinois water went to Britain, the British water went to Illinois, and guess what? They reversed their results with the water. And it turned out the distilled water that one of the labs was using was not quite distilled. You know. And I'll finish up with this guy named Mark Spector. And Mark Spector was a student in Cornell. And he started getting these results that showed basically how cancer starts. And not only could no one else reproduce it, he was such an outstanding student that his advisor, who was a professor, retired so that Spector could take his job at Cornell. And it turned out it was all faked. It was all faked. And then they started looking back, and when Spector was a master's student, you know, I told you it'd be great if we could separate out the oxygen binding from CO2. That's what he did for his master's degree. He developed an enzyme that would not bind oxygen, would only bind CO2. So he, you know, and once they started looking at that, they said, okay, that's not possible. You know, so I don't think the take-home story is you're going to fake results. Don't cure cancer or make plants be much more efficient than they really are, because, you know, if you're not going to get caught, you're going to be disproven. Okay? Any questions? Okay, I'll see you on Friday.